Okay. Let me share my screen. And yeah. So we were discussing two-user discrete memoryless broadcast channels in the last class, and
Oh,
we were deriving inner bounds on the same, right?
sir,
Uh, yes, yes, please.
like before starting, can you just once discuss the homework too, sir? Like,
So I will post solutions for both homework 1 and homework 2 maybe by early next week.
oh, okay, sir.
So if you have any questions after that, we can discuss it later.
Oh, okay, sir.
Right? Okay. So yeah. So the thing we were discussing two-user discrete memoryless broadcast channels, and in particular, we were discussing the superposition coding inner bound. So in this class, I'll prove the superposition coding inner bound for a general discrete memoryless broadcast channel. Uh, but we see that this in fact this inner bound turns out to be the exact capacity region for degraded broadcast channels. But for general broadcast channels, you can in fact do better. For non-degraded broadcast channels, there are better schemes and which give better inner bounds. So the rate region will in fact be larger than what we derive over here. Okay, and so this is the statement of the superposition coding inner bound. So if you have uh, a, a general two-user discrete memoryless broadcast channel specified by the conditional or the transition probabilities y1 given x and py2 given x, then we say that a rate pair R1 R2 is achievable. So the superposition coding scheme guarantees that R1 R2 is achievable as long as we can find some joint distribution pxu over x and some auxiliary alphabet u such that R1 is less than I x y1 given u and R2 is less than I u y2 and R1 plus R2 is less than the mutual information I x y1. Okay. And it turns out that these auxiliary random variables are important. So if you don't have these auxiliary random variables, then you can't really achieve a better scheme. And in the context of superposition coding, the auxiliary random variable also has a physical interpretation, and the interpretation is that U is essentially the message for user 2, right? Or in some sense, the UN correspond to the cloud centers of the superposition code, whereas the XNs correspond to the satellite code words of the superposition code, right? So this expression for the rate region is kind of intuitive. It ensures that so we're generally assuming that user 2 is degraded with respect to user 1, but even otherwise, even if there's no degradedness, what the superposition coding scheme ensures is that user 1 can decode both the cloud center and the as well as the satellite code word, whereas user 2 can only decode the cloud center. So as long as R is less than IUY2, user 2 can decode reliably. User 1 can decode as long as R1 is less than IX1 given U, and R1 plus R2 is less than IX1, XY1. So this condition guarantees that uh, user 2 can decode both the so this condition guarantees that user 1 can decode the cloud center, and this ensures that given that the cloud center is decoded correctly, user 1 can decode the correct satellite code word. Okay, so that is the broad that's the statement of the superposition coding inner bound. So in this class, I will prove this. So we'll prove it using using a random coding argument, and then we'll evaluate the superposition coding inner bound for some discrete memoryless broadcast channels. So mainly binary input, binary output broadcast channels, which are not necessarily sort of symmetric or anything of that sort. All right. But before we start, before I actually get into the details of all of these, are there any questions? Okay, so we've seen before for the discrete for the binary symmetric broadcast channel, the geometry of the superposition code is as follows. You generate a bunch of cloud centers, and for each cloud center, you generate a bunch of satellite code words, and what you transmit are the actual satellite code words. User 1 is able to decode both the satellite code word and the cloud center uniquely, and you want to ensure that user 2 can decode the cloud center reliably. Right, so the superposition code essentially looks like a bunch of clusters. So these are all subcodes corresponding to each cloud center. So you can think of them as different clouds with a cloud center and a bunch of satellite code words. So, so the geometry is in the following manner. Okay, and so the way the code book is generated for general discrete memoryless channels or discrete memoryless broadcast channels is the following. You fix a joint distribution pxu. So if you fix an alphabet u, some finite alphabet u, and you fix a pxu on x cross u, such that the following conditions are satisfied. So you also fix an epsilon greater than 0 and take R1 to be this mutual information minus epsilon, R2 to be this mutual information minus epsilon, and R1 plus R2 less than or equal to this mutual information minus epsilon. So you fix any R1, R2 which satisfies these properties. Okay, and we'll show that this particular rate pair is achievable. Okay, now, so yeah, it's a little more tricky. So fix any rate pair such that these conditions are satisfied. Okay, as long as these three conditions are satisfied, we can show that the probability of error vanishes with n. Okay, so once you fix a pxu and an r1 and r2, you now generate the code book. Okay, and the code book, as we did before, will be generated randomly. So we'll analyze a random code book and show that if you take a code book at random, then there is at least one code book among this set of all possible code books which performs well. Right, and the way we generate the random code book is as follows. So you independently generate 2 to the nr2 many cloud centers. So essentially you pick 2 to the nr2 many vectors, un of 1 up to un of 2 up to un of 2 to the nr2, where each cloud center is drawn with IID components distributed according to PU. Okay, and given a particular cloud center, for each cloud center, you generate 2 to the nr1 many satellite code words. And how do you generate the satellite code words? They're generated independently according to px given u. Right, so the jth satellite code word in the ith corresponding to the ith cloud center or the ith cloud has whatever n components, n entries, where each entry is drawn independently according to px given u of of x given ut of I. So this conditioning is on the cloud center. Okay. So this is how the code book is generated, and how is the encoding done? So the encoder does the following. Suppose you want to send message M1 to user 1 and message M2 to user 2. Then you generate the M1th satellite code word in, sorry, I guess there was a mix up over here. So the first I denotes the cloud center and J denotes the satellite code word. So if you want to transmit M2 to user 2 and M1 to user 1, then you transmit the M2th satellite, sorry, the M1th satellite code word in the M2th in cloud M2 or corresponding to cloud center M2. Right? So this identifies the cloud center or the cloud, and given a particular cloud, this indicates which satellite code word is transmitted. Okay, and the picture to keep in mind is the following. Uh, so if you maybe label these clouds as 1, 2, 3, 4, 5, and 6, then if you want to transmit, say, uh, message say 7 to user 1 and message 5 to user 2, so the fifth message to user 2 and the seventh message to user 1, then you look at the fifth cloud center, which is this one, and the seventh code word in this cloud center. So maybe if you fixed some numbering 3, 4, 5, 6, 7, 8, 9, 10, then basically the transmitter would send this particular code word over here. Right? So this code word would be transmitted across the channel. Okay, so it's sent to both users. Now the users, so user 1 gets y1n and user 2 gets y2n, and then they try to decode to the closest to the corresponding code word. And the decoder works as follows. User 2 is only required to decode to the cloud center and doesn't really need to identify which satellite code word was transmitted. So it tries to find a cloud center which is jointly typical with the received sequence. So you look at all possible cloud centers in the codebook and then try to and see if there is a unique cloud center which is jointly typical with respect to y2n. If there is a unique such cloud center, then you declare the corresponding message as the one that was transmitted. That is the estimate. If not, if there are more than one cloud center which are jointly typical with respect to y to n, or if there is no cloud center which is jointly typical with respect to y to n, then you declare that it's an error. Okay, or you just declare that the first message was transmitted. All right. So this is what user 2 has to do, or the second decoder has to do. Decoder 1 does the following. So the first decoder, user 1, will decode both the satellite code word as well as the cloud center. So it tries to find that particular satellite code word and cloud center, which are jointly typical with respect to the received vector yn. Right? And so if there is a unique such satellite code word and cloud center which are jointly typical with respect to y1n, then you declare that to be then you declare the corresponding I to be the correct message. If not, then you declare maybe message 1 was transmitted. If there are multiple code words and multiple cloud centers, or if there is no code word or cloud center which are jointly typical with respect to yn, then you declare that maybe the first message was transmitted. So that can potentially constitute an error. Okay, and so in some sense you're basically giving up if you cannot find a unique uh, code word which is jointly typical with respect to the received sequence. Okay, so this is how the encoder and the decoder works, and now we'll analyze the probability of error. Right? So what are all the sources of error? So an error occurs uh, if 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 the actual transmitted sequence or the cloud center and the code word are not jointly typical with respect to the corresponding received vectors. Okay, and we certainly know that. Uh, so So sources of error. So the first case is when the actual, so let's assume that without loss of generality, that the first message was transmitted. So M1 equal to 1 and M2 equal to 1. And because all the code words are generated in an identical fashion, there's no loss of generality in assuming that the first message was transmitted. So what can go wrong? The first thing that can go wrong for user 1, or let's start with user 2. So un of 1, comma yn, y2n are not jointly typical. N of p u y2. Okay, so this is what might happen, and the same thing can happen for user 2. So xn of 1 1, un of 1, y1n are not jointly typical. So this is one source of error. The second source of error is the second kind of error which can happen is that there is an erroneous code word which is jointly typical with respect to the received sequence. So, for user 1, sorry, for user 2, let's say un of I is in the typical set. And this happens for some I which is greater than 1, right? Something which is not equal to the first one. So there's some other code word corresponding to a different message which is jointly typical with respect to the received sequence. So if you think about it in terms of, say, binary symmetric channels or in terms of Gaussian channels, what this means is that there is some other cloud center which is closer to the received or which is close to the received sequence when compared to the actual transmitted sequence. So the first statement essentially says that the transmitted sequence is far away from the received sequence for user 2, and this statement says that there is some other code word corresponding to a different message which is close to the received sequence. Okay, that's one way of interpreting this for specific cases such as the binary symmetric broadcast channel or the Gaussian broadcast channel. Okay, so this is for user 2. For user 1, there is some other, so different things can happen. So you can have xn of, this is the first cloud center. So the cloud center may be decoded correctly, but the but within the same cloud center, you could decode to a different uh, code word, different satellite code word. So the cloud center is decoded correctly. So the cloud center is decoded correctly, but the satellite code word is decoded incorrectly, or both the cloud center and the satellite code word are decoded incorrectly. Correct. So these are the kinds of error that might happen. So if user one, so this is for user one, this is user one or receiver one, and these are for, this is also for user one, whereas this is for user two, this is for user two. Right? If none of these happen, then it means that you decoded correctly. So it means that the correct code word is typical. So if none of these two happen, then it means that the correct code words and the correct cloud centers are jointly typical with respect to the received sequences. And if none of these happen, it means that both the cloud center, so this means that there is no other code word or there is no other cloud center which is jointly typical with respect to the received sequence. So in other words, if you look at the binary symmetric channels, it means that there's no other code word which is close to the received sequence, and the correct code word is indeed close to the received sequence. Okay, so these are the sources of error, and and uh, and as long as we show that each of these probabilities are vanishing in n, we can just use the union bound to show that the overall probability of error is vanishing in n. So an error occurs if any one of these events occur. So it is the union of this event and this event, this event, this event, and this event. Okay, so it's a union of multiple events. Note that each of these events consist of multiple sub-events. So it can be joint, so y2n can be jointly typical with respect to un of 2 or un of 3 or un of 4 and so on. So there are multiple sub-events over here. But essentially what we're going to do is we'll just use a union bound. So it will be upper bounded by the sum of the probabilities of any of these events happening. And as long as that probability is vanishing in n, the overall probability of error is also vanishing in n. All right. So any questions so far? Okay. So let's look at let's look at these three things. All right. What can you say about the probability of this happening? So you know that un of 1 is drawn IID uh, according to PU, and this is transmitted. This is, of course, from this you generate xn of 1 according to Px given you, and transmit xn of 1 comma 1 through the channel to get y2n. Right. So these two. So if you look at the joint distribution of these two, these are IID according to PUY. Right? So UN of 1 and Y2N is jointly distributed, and it's IID PUY. Okay. So since these two are IID PUY, what is the probability that this sequence is not, so these two sequences are not jointly typical? Yes, anyone? So you have UN of 1 and Y2N, which are jointly distributed IID according to PUY2, and you want to know what is the probability that this pair is not in T epsilon n of PUY2.
2 power minus n into some
Correct. So 2 to the minus n times some epsilon square,
epsilon.
some constant.
Yes.
Right, so let me call this E11, E12. So the probability of E11, this is less than or equal to whatever 2 to the minus n epsilon square times some constant, say alpha 11. Okay, so similarly, if you look at this particular sequence, this triplet of sequences, you know that xn also each code word is generated IID. So these are IID P X U Y1. Correct. You're first generating UN IID according to PU, and then xn of 1 1, which is independent. Each component is independent but drawn according to Px given U, and y1n is obtained by passing xn of 1 comma 1 through the channel py y1 given x. So overall, the components are all IID drawn according to Px U y1. So similarly, the probability, just as in the first case, the probability that this occurs, that they're not jointly typical, is again some quantity which is exponentially decaying in n. So it's n epsilon square times some alpha 1 2, where alpha 1 2 is a constant which depends on p x u y1, but nothing else. It doesn't depend on n, it doesn't depend on r1, it doesn't depend on r2. Okay. All right, so now we have some more events. So let me call this E21, E22, and E23. The reason why I'm distinguishing the first set of events from the second set of events is that the first set of events don't really depend on R1 or R2, whereas the second set of events, all of these depend on, crucially, on R1 and R2, and these are really what give you the bounds on the rates. Okay, so it's only if R1 and R2 are sufficient, are not too large, that these probabilities vanish with n. And as before, we'll to prove all of these, we'll invoke the packing lemma that we proved a long time back. So the packing lemma says the following. So if we have, let me just call it y tilde n u tilde n, which are drawn IID according to p y tilde u tilde, then and I draw 2 to the nr many sequences. Let me call them x tilde n according to some conditional distribution px given x tilde given u tilde. So each of the x tildes are correlated with u tilde, but they're independent of y tilde given u tilde. Right? So they depend on u tilde, but not they're not jointly correlated with respect to y tilde, conditioned on u. Right? So as long as the packing lemma says, as long as the rate is not too large, as long as the number of these sequences is not too large, if r is less than the mutual information between x tilde u tilde given u x tilde y tilde given u tilde, the probability that all these three are jointly typical is vanishing in n, and it's in fact exponentially decaying in n. So the exact constants over here don't matter. All that matters is that these depend on epsilon in some fashion. Okay. So this is the packing lemma, and we'll use the packing lemma for each of these three events by identifying a suitable p x tilde y tilde u tilde. Okay. So let's look at them one by one. So let's look at E21. All right. So here, so y2n is obtained by passing un of 1 through the channel, but un of I for I not equal to 1. So these are independent of un of 1 and therefore independent of y2n. So un of I y to n. So these are actually independent sequences because all the other code words are generated independently of the first code word, and y to n is obtained by passing the first code word through the channel. Right? So these are, the components are all IID, but they're not distributed according to PUY2, they're distributed according to PUPY2. Right? They're independent. Correct? So here UN and Y2 are independent of each other. So now we need to invoke the packing lemma, and in this case we'll take U tilde to be empty, X tilde to be equal to U, and Y tilde to be equal to Y. Right? So this says that as long as R2, which is the number of UNs which are generated, as long as this is less than the mutual information between X tilde, Y tilde given U tilde, which is equal to the mutual information between U and Y given the empty, so this is I of UY, the probability or this minus sum delta of epsilon, the probability of error is vanishing in it. So the probability that e to 1 occurs is less than or equal to 2 to the minus n some delta prime of epsilon. Right? You may call it delta 2 1 of epsilon. Okay, so as long as R2 is less than IUY minus something sufficiently small, generally this is less than epsilon. So as long as this is true, this probability is vanishing in it. So let's look at E22. So now I want to know what is the probability that this happens. So user 1 can decode, user 1 decodes the correct cloud center, but the incorrect satellite code word. All right. So now these are, so note that UN of 1 is, so xn of 1 comma j depends on UN of 1, but conditioned on UN of 1, y1 of n and xn of 1 comma j are independent of each other. Right? So these are distributed according to PU, Px given U, Py given U. Right, so maybe I should. So it's Px given U, Pu, Py given U. Right, because xn of 1 comma j, this is the first cloud center, and this is some other code word, maybe the second or the third or the 10th code word in the first cloud center. So this is dependent on UN, but you're actually transmitting the first first satellite code word in the first cloud center. So y1n is independent of xn 1 comma j for j not equal to 1. So if you want, so now we want to invoke the packing lemma, here x tilde is equal to x, u tilde is u, and y tilde is equal to y. So as long as R1 is less than the mutual information between x tilde, y tilde given u tilde minus delta of epsilon, which is I x y given u minus delta of epsilon, this probability E22 is also vanishing in it. E22 is exponentially decaying in it. And maybe let me call it delta 22 prime of epsilon. So it depends on epsilon. It can depend on R1 and R2, but otherwise it is independent of n. Right? So similarly, E23 we have xn of I comma j un of I yn. So you get both the cloud center and the satellite code word wrong. Right? So note that yn depends on xn of 1 comma 1. It's obtained by passing xn of 1 comma 1 through the broadcast channel. So all of these are independent of y1n. So this is px u, if I can call it px given u, pu, py. Right? So y does not depend on this un of I or xn of I comma j for I not equal to 1 and j not equal to 1. Correct. So here we identify x tilde as x comma u tilde is empty, and y tilde is equal to y. Right. So as long as the total number of such sequences is 2 to the nr1 times 2 to the nr2, right? That you generate those many xn un pairs. So as long as R1 plus R2 is less than the mutual information between X, U, and Y, which is, yeah, so as long as this happens, the probability of E23 is also vanishing in it. It's exponentially decaying in it. Right? So basically what we've shown is as long as the rates satisfy these conditions, so as long as R2 is less than IUY, strictly less than IUY, as long as R1 is less than the mutual information between X, Y given U, and as long as R1 plus R2 is less than the mutual information between X, U, and Y, the probability of error is vanishing in it. Now this looks almost the same as we started off with, except for a small change. So certainly the first condition is satisfied, the second condition is satisfied exactly, but the third condition looks a little different. We chose R1 plus R2 to be less than or equal to IXY1 minus epsilon. Whereas here we are getting that R1 plus R2 should be less than IXU and Y1. Alright, so this looks a little different, but what we want is we have chosen R1 plus R2 to be less than IXY1. And it turns out that this is simply equal to IXY1 itself. So let's see why that is true. The mutual information between X, U, and Y1 is equal to H of Y1 minus H of Y1 given XU. So the crucial point to note here is that U, X, Y1, they form a Markov chain because you're generating the cloud center. For a given cloud center, you're generating the satellite code word, and the satellite code word is passed through the channel. So given the satellite code word, the way the cloud center is generated and the received sequence, they are conditionally independent of each other. Right? So therefore H of Y1 given XU is equal to H of Y1 given X. h of y1 minus h of y1 given x, because this forms a Markov chain. So this is just I x y. Okay, so that's good. So this ensures that all the conditions are now satisfied. We have chosen the rates which satisfy these three conditions. So all of these probabilities, each of these probabilities are exponentially decaying in n. By the union bound, the overall probability of error is less than or equal to the sum of these five probabilities. And since each of these probabilities is exponentially decaying in n, the sum of these five quantities is also exponentially decaying in n. Right? So the overall probability of error is also vanishing in n. All right. Any questions? So just to do a quick recap, we generated the superposition code by independently generating 2 to the NR2 cloud centers. For each cloud center, we generated 2 to the NR1 satellite code words and passed the satellite code word, passed the corresponding satellite code word through the channel and this depends on the message. Right? The decoder user 2 decodes to the cloud center, whereas user 1 tries to decode both the cloud center and the satellite code word. And the overall probability of error, just by using the properties of typical sets. So the first set of the first to bound the first two error events, we just use properties of joint typicality, and to bound the second set of error events, the probabilities of the error events, we just use the packing lemma by identifying the corresponding distributions. And therefore, as long as all the three rate conditions are satisfied, the probability of error is exponentially decaying in it. Okay, so this gives a proof that superposition codes achieve this particular set of rates over any general discrete memoryless broadcast channel. Okay, now this may be optimal, it may not be optimal, but it certainly gives us something to work with. And in fact, it will turn out that this is always better. This can be no worse than just using, for example, TDMA. So this in general will beat TDMA, but there could potentially be a better scheme. So in particular for non-degraded broadcast channels, for general broadcast channels where one channel is not stronger than the other in some sense, it will turn out that we can do much better than superposition coding. There's a separate scheme which is called Martin's scheme, which gives a better set of rates. So the inner bound obtained using that scheme will be better than the inner bound obtained using superposition codes. Okay, so this gives us a set of rates. So now let's maybe take a look at what rates are achievable for some example channels. Okay, so any questions so far? Okay, so let's see what we have so far and how do we evaluate it. So now the goal is to somehow numerically compute the rate region. Okay, so we will stick to only degraded broadcast channels for now. So And I'll just mention why we're sticking to degraded broadcast channels. So to numerically compute the rate region, what do you need to do? You need to first identify a suitable, so we'll get a bunch of rate points, and then we'll take the convex cover of those rate points that we obtain. So first, you need to identify what P ux we're going to choose. Right. The first step is to identify PUX, but for that we also need to identify the alphabet U. So how large should the auxiliary alphabet be? So it turns out that for degraded broadcast channels, for stochastically degraded broadcast channels or physically degraded broadcast channels, the size of U can be chosen to be less than or equal to the max of the size of X, size of Y1, size of Y2 plus 1. So for example, if both the inputs and the outputs are all binary, then the auxiliary alphabet can be taken to be ternary. Okay, so you fix a particular PUX, so maybe we draw PUX randomly, or you somehow look at all possible representative PUX, and once you get a particular PUX for a number of PUX, you want to evaluate achievable rate pairs. Right, so you then compute given PUX. So the channels are already given to you. PY1 given X and PY2 given X are already given to us. And for this channel, we want to evaluate the rate region. So given PUX, we can now compute the mutual informations. Let me call it I1, which is I X Y given U. Compute I2, which is I of uy, and I call it I12, which is I x. Sorry, this should be xy1, xy1. Correct. So as long as R1 should be less than or equal to I1, R2 should be less than or equal to I2, and R12 should be less than or equal to I12. Right, so as long as these conditions are satisfied, we know that the rate pair is achievable using superposition codes. We've just derived that. Okay, so but now we compute these three quantities, and now we have to choose some points, some set of points which satisfy these three conditions. Right, so in general, these conditions will look like this. Right, so the first condition will look like, we'll say R1 is less than or equal to I1, sorry, R1 is less than or equal to I1, which will give us this line. R2 is less than or equal to I2, R2 equal to I2 gives us this line. And R12 is less than or equal to I12. Now this, you need to be a little careful. So it could be, depending on what I12 is, it could be either a line like this, which is a pentagon, which gives us a pentagon, or if I12 is really small, then it could potentially also give us something like this. Right? If I12 is less than I1 or I2, then you could get something like this, or maybe even something like this. Correct. So one way to get a rate region is we have R1 to be less than or equal to. So for this we have to identify all of these points, which is R1 is less than or equal to So this means that the following rate pairs are certainly achievable for a given I1, I2. So the min of I1, I12, comma 0. This is one achievable rate pair. Min of, 0, comma min of I2, comma I12. This is an achievable rate pair. Right, so this is I1, this is I2, this is I1, and this would be I12, if that is the case, or this could be I12, this could be I12. So whichever is smaller, that comma 0 is achievable. All right, so these give us 2 points, the intercepts on the x-axis and the y-axis, or the R1 axis and the R2 axis. And now we need to identify whether this is a pentagonal region or not. So I1, comma I12 minus I1. So this is potentially an achievable rate pair, but it's also possible that this itself could be too large. Right? So third condition is that this line looks something like this. So we need to take into account all of these conditions. So if this is the case, if the R12 line or the I12 line is too far away, then really this is the rate point which is achievable. Right, so it's the min of I12, comma I1 and I2, and similarly you get min of I12 minus I2, comma I1 and I2. All right, so these are all achievable pairs. So you get these 5 points. If it is indeed, so there are different cases. So this is case 1, the good case, in which case we have I1, comma 0, 0, comma I2, I1, comma I12 minus I1, and I12 minus I2, comma I2. Right? So I1, comma 0 would be this point, 0, comma I2 would be this point, I1, comma I12 minus I1 would be this point, and I12 minus I2, comma I2 would be this point. Okay, this is the first case where it's indeed a pentagon, where this line intersects these two lines somewhere in between. But now there are other cases as well, and at least for degraded channels, this case is potentially possible. The other two cases don't arise for degraded broadcast channels, but can happen in the case of non-degraded broadcast channels. So the rate region may be a square instead, or it may be a rectangle instead of a pentagon. So in that case, you need to take the min of I12, comma I1 and I2. So this is the case where I2 is less than the I12 minus I1. So there are some special cases that essentially we need to take care of. All right. So let's see what these expressions look like. So if we just try to evaluate it. Right, so I've written a Python script to do all of, to compute the rate region. So it's similar to what we did for the multiple access channel. I have some helper functions to compute the KL divergence, or essentially to compute a mutual information, and then I have a function which, given these distributions py1 given x, py2 given x, and pux, computes I1, I2, and I12. Okay, so it returns I1, I2, and I12. Okay, so I've already written functions about this. You can I'll post all of this code on Piazza, so you can take a look. Okay, so now that we have this, let me generate a degraded broadcast channel. So I'll choose all the alphabet to be binary. I'll generate a random py1 given x, and I'll generate a py2 given y1. So py2 given x is just the composition of py1 given x and py2 given y1. So this part generates the channel. Okay, so this part generates the channel. So the channel transition probabilities are the following. So this is py1 given x, and this is py2 given x. So just by looking at this, you can see that the second channel is in some sense worse than the first channel, because in the first channel, it is more likely that a 0 remains a 0 and a 1 remains a 1, whereas in the second channel, it's more likely that a 0 becomes a 1 and a 1 becomes a 0. Right? So clearly the second channel is degraded with respect to the first channel. But this is not a binary symmetric broadcast channel, it's an asymmetric broadcast channel. Okay. So this is what this particular piece of code does. And now for a given broadcast channel, for a degraded broadcast channel, we'll just add rate points. Right? So the rate points are I1, 0, 0, I2, I1, min of these two, and the min of these two, I2. Because this part computes the rate pairs. So for any given distribution PUX and channel PY1 given X, PY2 given X. All right. So we can do two things. Either we can just generate some random PUX and then try to just compute rate pairs. So that is what this part of the code does. So let's plot it out and see what happens. So you get a bunch of points, right? And if you compute the convex hull of these, it looks something like this. Okay. But it turns out that if you try to do it using this approach, if you try to generate points PUX randomly and try to compute the rate points, it doesn't work that well because you'll be missing many rate pairs. So certainly this region is achievable, but it is not the set of all rate pairs which are achievable using superposition coding. So for this, you need to sort of take a grid for PUX and then compute the rate point. So note that here the maximum of R1 of R2 is something around 0.14115 or so. But if I take a grid, if I try to iterate over possible PUXs, then I get something better. The only flip side of doing that is that you have to iterate over a large number of PUX, and therefore the larger the size of the alphabet, the more the computational complexity. So this will take some time. Again, you need to take a finer grid to get a better so that you get a better resolution, but for this particular example, it turns out that this is enough. So if you have a large broadcast channel or a slightly more complicated broadcast channel, you need to run this over a very large number of iterations, and the computation complexity very easily blows up. So this is in fact the complexity of computing the rate region grows exponentially in the alphabet sizes of U and X. So even if it can be as large as 10 to the 6 or 10, even for binary case, it could be as large as 10 to the 6 if you want to do it more carefully. Okay, but for this particular example, I'm taking a very coarse grain. So this really gives you the set of all points which are achievable. So you get more points over here when you compare this to this. So here it goes only up to 0.15, whereas here it's going all the way up to 0.1819 something. Right. So the black region, or the region enclosed by these black lines, indicates what is achievable using superposition codes. And the red line indicates what is achievable using time sharing. So if you did time sharing, then anything below the red line is achievable. Whereas superposition coding can do something better. It lets you achieve this region in between. So any rate pair in this black region is achievable using superposition codes, whereas TDMA would give you something much smaller. All right. So you can play around with this code. I'll post it on Piazza and see what you get. You can try different channels, sometimes non-degrade, but note that this code mostly works only for binary input, binary output channels, and the complexity can grow very quickly. So just be mindful of that. But for any general binary input, binary output broadcast channels, you can run this code, but just by changing this part over here, changing just this part over here, and you can just experiment what happens. So if it is non-degraded, then this is not an optimal rate region, but for a degraded broadcast channel, this turns out to be exactly equal to the capacity region. The black curve is exactly equal to the capacity region. All right. So we'll stop at this point. So if there are any questions, I can take them now. Any questions? Okay, so if not, let's stop. So we meet again next week. So see you then.